All right, we're back now and moving on to finding empirical and molecular formulas from percent composition. Very often, chemical analyses of various types will, instead of actual masses, they will give you a data that will allow you to find the percent composition of a compound. And so this kind of ties into where we started in this section of the chapter. So for example, if you are investigating a compound made up of sulfur and oxygen, and you know from other data that it has a molecular weight of 80 grams per mole and is 40% by mass sulfur and 60% by mass oxygen, what are its empirical and molecular formulas? Okay, well, whenever the solution to this problem is very similar to the one that we just did. The only difference really is that we're given percentages of the elements involved rather than specific amounts of the elements involved. But of course, in order to get the empirical and molecular formula, you need to find out how many moles of each element are present. And so just having a percentage presents us with a bit of a problem, because in order to find moles, we need a mass. But as it turns out, that's actually pretty simple, much more simple than it might appear anyway, because if you have percentages of the elements, then all you have to do is assume a mass for the sample, and then you can find the percentages of that mass. And you can do that, and it doesn't matter what mass you choose because of the law of constant composition. That is, each compound will always be made up of the same number of atoms of the same elements, no matter how much or how little of it you have. So it doesn't matter if you're looking at 1 molecule of it or 10 tons of it, it'll still have the same molecular and empirical formula, and it will still be made up of the same percentages of the various elements that are in it. So whatever mass you assume for this sample of the compound, 40% of that mass will be sulfur and 60% of that mass will be oxygen. Well, if you're dealing with percentages, the obvious mass to assume would be 100 grams, because 40% of 100 is 40 and 60% of 100 is 60. You could assume any other mass you wanted. You could assume that the sample is 17 grams if you want, but then you have to find out what 40% of 17 is and what 60% of 17 is. And you can do that, but why make things harder than they have to be? So if you just assume 100 grams, the percentages become grams. So 40% sulfur out of 100 grams means 40 grams of sulfur. And if you have a 100-gram sample, 60% of it is oxygen by mass. That means you've got 60 grams of oxygen total in that 100-gram sample. And now things are just basically the same as what we just did. Finding the moles, you would take the 40 grams of sulfur and divide by the molar mass of sulfur from the periodic table, which is 32 grams per mole. Or again, it's easier to watch the units if you multiply by 1 over the molar mass, which would be 1 mole of sulfur for every 32 grams. That way it's clear that grams of sulfur cancel, and that leaves you with moles of sulfur as the unit for the answer. And then you do the same with oxygen, 60 grams of oxygen times or divided by the molar mass of oxygen, which would be 16. Or you can multiply by 1 over the molar mass, which would be 60 grams times 1 mole of oxygen over 16 grams of oxygen. And here again, grams of oxygen cancel, and you end up with 3.75 moles of oxygen. Then you need the relative moles of the elements relative to each other. And so you just divide both of those numbers of moles by whichever one is smaller. So 1.25 over 1.25 obviously is 1. 3.75 over 1.25 is 3. So your empirical formula is SO3. That's the empirical formula, the one that you get directly from the experimental data. Now, for the molecular formula, you would need to add up the molecular mass of the empirical formula and compare it to the molecular mass of the compound. and see how they compare. So when you take the molar mass of sulfur from the periodic table, we'll round that to 32, plus 3 times 16 for the oxygens, you end up with a molar mass of 80 grams per mole. And that happens to be what the molecular mass is, 80 grams per mole. And so if you take one divided by the other, you get 1. And that just means that the molecular formula is the same as the empirical formula. And that does happen quite often. So you're done. So hopefully that doesn't provide too many challenges there. There will be some homework problems on that you can do to practice that a bit. And the next section deals with a topic which is very important in chemistry. It's really, really important that you understand the concept of molarity, because it's something that we come back to over and over and over again throughout throughout the rest of the semester, both in lecture and in lab. Molarity is, as the name kind of implies, it does involve moles, but it's a unit of concentration. A unit of concentration is a way where you express basically how much stuff is dissolved in a solvent. So we're talking here about solutions. A solution, if you recall, is just a homogeneous mixture. It means a mixture of 2 or more different substances where the substances are present in the same container at the same time, but they aren't chemically bonded to each other. So kind of like salt water. The salt and the water are both in the glass at the same time, but they're not bonded to each other. So in other words, there's more than one compound in there. And it's a homogeneous solution if the substances that are mixed together evenly. If you can't tell any difference between one part of the solution and any other part of the solution. If you take a glass of water and mix in some salt, unless it's a really huge amount of salt, the salt will dissolve and it will mix in homogeneously with the water, meaning that the salt water will be just as salty at the top as it is at the bottom and in the middle. Now, it's still possible that you could have another glass of salt water that has more salt or less salt in it. So the composition of homogeneous mixtures can vary from one sample to another. But the thing about homogeneous mixtures is the composition cannot vary within the mixture. It's the same everywhere within any given sample. And so that would be a homogeneous mixture or a solution. A homogeneous mixture is made up of at least 2 components. One is known as the solvent, and that is usually whichever substance is present in larger quantities. And it just so happens in general chemistry that most often the solvent will be water. But there are all kinds of examples of things where the solvent might be something else. If the solvent is water, then the solution is known as an aqueous solution, or the little AQ in parentheses. And also in a solution, you will have at least 1 solute. It's possible that you could have more than 1 solute, but the solute is the stuff that's dissolved in the solvent. And the solute is usually identified as being the substance or substances present in smaller quantities. And so some examples of homogeneous mixtures or solutions would be, say, salt water, where the salt mixes evenly in the water. Air is an example of a homogeneous mixture, as it turns out, because of the nature of gases, anytime gases mix together, they always mix homogeneously. And so technically that means air is a solution. Air is made up of several different gases. About 79% of air is made up of nitrogen. So nitrogen would be considered the solvent. And the rest of it is made up of about, say, 20% oxygen and tiny little percentages of things like water vapor and carbon dioxide and even a little argon. And so they would be the solutes. So you can have a solution that's entirely made up of gases. Metal alloys are also considered to be solutions because they are homogeneous mixtures. Metal alloy, would be something like, say, brass. If you want to look at, brass, like most keys are brass. And brass would be made up of mostly copper with some zinc thrown in. And so in that case, the copper would be the solvent and the zinc would be the solute. And the way that you can get solids, basically the only way that you can get solids to mix homogeneously would be if you melt them and mix them together as liquids and then cool them down so they turn solid again. And that's exactly how they make alloys like brass or steel or bronze. There are a lot of different alloys out there. You can never get a truly homogeneous mixture of solids as solids, because in order for the mixture to be homogeneous, the particles have to be what they call intimately mixed with each other. So in other words, they have to be mixed with each other evenly on the level of individual atoms and molecules. And if you try to take, say, a piece of copper and a piece of zinc and you file them down into really, really tiny solid particles and mix them together, it's still not going to be homogeneous, because each of those tiny little particles, if it's big enough for you to see it, it's going to consist of billions and billions of atoms of copper or zinc. And so there will be large parts of the mixture where it's nothing but copper. Each little grain of copper is nothing but copper, and each little grain of zinc is nothing but zinc. They have to be mixed together on the level of individual atoms and molecules. And so the only way to do that is to melt them. That allows the individual copper and zinc atoms to move around individually and to mix together individually. And then you can cool it down and they kind of get frozen in place. And then you have a homogeneous mixture of solids. So, like when you dissolve salt and water, first of all, salt ionizes into sodium ions and chloride ions, and then they move around in the water as individual ions, and they can mix evenly in with the H2O molecules. Same with the air. The oxygen molecules in the air can move around freely and individually in among the nitrogen molecules, so that's a homogeneous mixture. Sugar and hot tea would be a homogeneous mixture also, because sugar dissolves very readily in hot water or hot water-based beverages like tea. And so the hot sugar in the hot tea will make the tea just as sweet at the top as it is at the bottom, and that's a homogeneous mixture. An example that would not be a homogeneous mixture would be, say, sugar in cold tea, iced tea, because if you put sugar in iced tea, most of the sugar just drops straight to the bottom and doesn't dissolve. So you've got an area at the bottom that's almost entirely sugar and very little tea, and then everything above that is going to be mostly tea and very little sugar. So the composition changes within the glass, and that would make it a heterogeneous mixture. Alcohol and water mixed together homogeneously. So something like vodka, which is essentially a mixture of just alcohol and water, that's a homogeneous mixture. Gasoline is a homogeneous mixture. If you do an analysis on gasoline, and if you're going to do that, I would recommend starting it early in the day, because it's going to take a while. There's a lot of stuff in gasoline, and it's all mixed together homogeneously. You can't see any differences from one part of a can of gas to another. The properties will be the same everywhere within the gasoline, and it's made up of just a bunch of different compounds that mix together really easily and really evenly. So for a homogeneous mixture, again, the composition has to remain the same throughout any one sample, but it can vary from one sample to another. Just like with gasoline, you've got premium gasoline, you've got regular gasoline. Back in the day, you had leaded gasoline. The composition could vary from one type of gasoline to another, but within any sample of one type of gasoline, it would have to be the same, the composition would be the same throughout. A concentration deals with solutions, and a concentration in general is just a way of expressing the amount of solute dissolved in a given amount of either the total solution or solvent. So you're comparing how much solute is there compared to either the total amount of solution or just the solvent, one or the other. So it's kind of like a percentage almost. So there are a lot of different ways to express concentration, and we'll see some of the others later, like percent by mass or mass volume percent or parts per million and stuff like that. But by far, the most important way to express concentration in chemistry is molarity. And molarity is defined as the number of moles of solute per liter of solution. Okay, so how many moles of the stuff that's dissolved in the solution will be present for each liter of the entire solution? The units of molarity are usually just given as moles per liter, or M/L, like that, or say actually MOL/L. And you can think of that as in practical terms, in terms that would allow you to calculate it relatively easy. You can think of that as being number of moles of solute divided by the volume of the solution in liters, or in other words, the number of liters of solution. And think of it like that makes it a lot easier to calculate what the molarity of a solution would be. So for example, if you had a saltwater solution and it has a total volume of 155 milliliters, and it contains 38.5 grams of sodium chloride, what is its molarity? Well, molarity, again, number of moles of solute, which is NaCl in this case, divided by the number of liters of solution. So those are the two things you have to find. The number of moles of sodium chloride is just going to be the mass of sodium chloride divided by the molar mass from the periodic table. Or you can just multiply it by 1 over the molar mass of the periodic table. That's what I've done here because, again, it makes it obvious how the units work out. 38.5 grams of sodium chloride divided by 58.5 grams per mole, or times the fact that there's 1 mole of sodium chloride for every 58.5 grams of sodium chloride. Grams of sodium chloride will cancel out, and you get 0.658 moles of sodium chloride. So that's how many moles of sodium chloride are in that solution. And again, 58.5 is what you get if you look at the masses of sodium, which would be 23, and the mass of chlorine, which is 35.45. I'll call that 35.5. Add them together, you get 58.5. So that's where that came from. And the volume of solution in liters is important also. I deliberately gave it in milliliters, which is the most common unit we use for measuring volumes of solution, but the volume doesn't need to be in liters. So that's just a conversion involving metric prefixes. So 155 milliliters times the fact that there's 1 liter for every 1,000 milliliters. Milliliters cancel, you get liters, and it's 0.155 liters. So then you just take your number of moles, 0.658 moles of NaCl, divided by 0.155 liters of solution, and that tells you that the molarity is 4.25. We would write that as 4.25 capital M. The symbol for molarity is capital M, so it's important that you remember to capitalize it if you're talking about molarity, because there is a different unit of concentration that we'll see later, which involves a lowercase m. So you do have to keep them straight. We would call this, if you were going to say it, a 4.25 molar solution. So if you say the solution is 4.25 molar, that just means the molarity is 4.25, or 4.25 moles of solute for each liter of solution. Okay, so molarity is number of moles of solute divided by the volume of the solution in liters. Of course, in many cases, you will know the molarity and you might not know one of these two quantities. How many moles of solute are required to make a solution of a certain volume with a certain molarity? Or say, if you've got a certain amount of solute and you want to make a solution of a certain molarity, what volume would it have to be? And for that, you can take advantage of the fact that molarity is essentially a three-term equation. And we've saw examples of these before in the first chapter. And that means that you can just set up a triangle and that will help you rearrange the equation when you need to. So if you have molarity is number of moles per liter, you can actually sort of make this a little bigger if you want to. Okay, this a little lopsided pyramid here. Looks kind of like the step pyramid in Egypt. Anyway, setting up a little pyramid or a triangle like this helps you rearrange the equation. So now if you know, say, the molarity and the volume of solution, the number of moles is just molarity times the volume of solution. If you know molarity and moles of solute, then the volume of the solution would just be moles of solute over molarity. And that's what we're going to take advantage of in the next couple of examples. So for example, what mass of sodium chloride would be found in 10 milliliters of the solution above? Okay, so we just found the molarity of the solution above, so we know that, and we know the volume. We're looking for mass, but in order to find mass, you normally go through moles when you're dealing with molarity. So that means that the first thing we have to find is number of moles. And then we can use the molecular mass or the molar mass, if you want to call it that, of NaCl to find the mass of NaCl. So we see from the triangle, if molarity is number of moles of solute divided by the liters of solvent, of solution, I mean, then number of moles of solute must be the molarity times the number of liters of solution. So in other words, moles of solute would be molarity times liters. Okay, so that's what that means. When they're next to each other, you multiply. So number of moles of sodium chloride would be 4.25 molar. And a lot of times in dealing with questions dealing with molarity, it can be very helpful to write out explicitly what the molarity means, whether you're looking for the molarity or whether you already have the molarity. 4.25 molar means 4.25 moles of sodium chloride per 1 liter of solution. And a lot of times when you write it out like this explicitly, it makes it easier to see what you need to do with that number in order to get the answer you want. For instance, even here, if you had forgotten to do the triangle, if you take the molarity and write it out like this, then it becomes pretty obvious what you need to do in order to find the number of moles in that solution. That is, you have to multiply the molarity by the volume in liters. That way liters will cancel and you'll get moles. And that's exactly what we end up doing. 4.25 moles of NaCl per liter of solution times the volume of the solution in liters. It was 10 milliliters. Remember to watch those units because volumes are usually going to be given to you in milliliters. So 10 milliliters divided by 1,000 gives us 0.01 liters. 4.25 moles per liter times 0.01 liters means that there are 0.0425 moles of sodium chloride in that solution. And then the mass is just the number of moles times the molar mass of sodium chloride. And again, you can see here that moles of sodium chloride cancel. And we end up finding out that in that volume of the solution, there are 2.48 grams of sodium chloride. Okay. All right, just one other quick example. What volume of the above solution would be required be required to use if you wanted to use exactly 10 grams of sodium chloride? So a certain volume of that compound will involve 10 grams of sodium chloride. That's the question. So volume, in other words, liters in this rendering, would be equal to number of moles divided by molarity. Okay, so we need number of moles in order to do number of moles divided by molarity, but we have 10 grams of sodium chloride. That's the amount we actually were given or asked about. So the first thing you have to do is find how many moles that is. And for that, you would take 10 grams divided by the molar mass of sodium chloride, or times 1 over the molar mass of sodium chloride. And this way you can tell that the units do cancel out. So 10 grams divided by 58.5 grams per mole, or times 1 over 58.5 grams per mole, means that we want 0.171 moles of sodium chloride. And as we saw before, if molarity is number of moles of sodium chloride divided by liters of solution, then liters of solution would be number of moles of sodium chloride divided by molarity. So we do that. The volume of solution in liters would be 0.171 moles of sodium chloride divided by 4.25 moles of sodium chloride per liter of solution. Doing it this way is the same as multiplying 0.171 moles of sodium chloride by 1 liter over 0.425 moles, because this is just the reciprocal of the denominator that we started out with. Doing it this way makes it easier to see how the units work out. Moles of NaCl cancel out, and that leaves you with liters of solution. And when you work the number out, it comes out to be 0.0402 liters of solution. And actually in the question, I just said volume. I didn't specify what units to use for volume. So you can actually leave it as 0.0402 liters because that's a volume. But I went ahead and changed it to milliliters because in practical terms, that's the unit you would be using to measure the stuff out. And it turns out it's 40.2 milliliters. But this answer would be perfectly acceptable. Okay. Well, that's enough for this segment of the video. So I'll stop here and we'll continue in a moment.